chapter 4, induction and recursion. The kind of thing we're going to be focusing on in this chapter is a sort of question. So suppose Pn is an open statement, and where the universe is the natural numbers, or in other words, the positive integers. So here's a question. I mean, it's a very general question, but how do we prove that Pn is true for all natural numbers n? So here's one thing you shouldn't do, right? You can't really just prove them all individually because there's infinitely many natural numbers. So you can't just, you can prove P of 1 is true, P of 2 is true, P of 3 is true, but that's going to get old pretty quick, right? So you need some sort of method for proving this statement for all n at the same time without having to, do every individual n. Actually, we have proven statements like this before. So earlier what we've done, we've seen actually quite a few methods for this. For example, a direct proof, right? Because, for example, for the, we use the direct proof to prove the statement that for all n even implies n squared even, right? This is something we've done. We've also seen contrapositive when we proved for all n that n squared even implies n even. Okay, this is just a reminder for things we've done a long time ago. We also saw proof by contradiction. So that we saw contradiction when we proved that root 2 is irrational. So let's say for all a, for all b, a over b is not equal to root 2. So this is in the universe of the integers, right? We've also seen a little bit of proof by cases when we proved that for all n, n squared divisible by 3 implies n divisible by 3. Okay, so we have proven things for all n many, many times. But what we're going to be talking about for the next little while, for this whole chapter, is another method which is quite different from these ones. So our new method, actually maybe I'll write this on the next board. So our new method that we're going to use, we're going to get some practice with, is called induction. Okay. So here's the basic concept of induction. So the idea is that if P1 is true, so remember P, we're thinking of P as being some statement, right? Open statement. Open statement with universe being the naturals. So the way induction works is that if P1 is true and Pn logically implies Pn plus 1 for all n at least 1, then Pn is true for all natural numbers n. The way I like to think of this is kind of like dominoes. You know dominoes, like these things, you flick one and they all knock each other over. So this is kind of like saying, okay, this is kind of like setting up your dominoes. This is like saying the nth domino will knock over the n plus first domino. And this is kind of like saying I flick my first domino. So it's like P1 is, so I mean, you can kind of think of how this works, right? So imagine P1 is true, and whenever P1 is true, P2 is true, right? So if you apply this for n equals 1, it says whenever P1 is true, P2 is true. So now you know P2 is true by modus ponens or something. And now suppose I know whenever P2 is true, P3 is true. Well, P2 is true, so P3 is true. And now if I know P3 implies P4, and I know P3 is true, then I know P4 is true, and so on and so forth. It's just kind of dominoes going on forever. So this is one way to prove that something is true for all n. You just have to show that it's true in the very first case. So actually, so here I'm talking about P1, but if we wanted to prove this for all n at least 100, what you would start with is P100, right? So if you can prove it's true for some smallest case, and then you can prove that every case implies the next case, then it's true for all cases after that. Any questions about this? This is like a high-level concept, but we'll see some examples. Okay, let's get right to an example right away. So. Okay, so I claim that for all, or let's say for any integer n at least 1, I claim that the sum 1 plus 2 plus 3 plus ... up to n is equal to n times n plus 1 over 2. Okay. So, and I want to prove this using this new toy, induction. So this new trick. So let's prove this by induction on n. First of all, is it clear what this statement says? So I've got this ... here, but I'm saying I'm adding up all the numbers, 1 plus 2 all the way up to n, and I'm saying this should equal this. And I want to prove this for every n. Yeah, for every n. Okay, so I'm going to basically follow these two steps. So I want to prove it's true for n equals 1, and then I want to prove whenever it's true for n, it's also true for n plus 1. And then I'll be done. So I'll start by proving it's true for 1. So this is so there's a sort of terminology for this called the basis of the induction. So here, this thing where P1 is true, this is called the basis for the induction. So we want to prove that this is true for n equals 1. So for n equals 1, the way I'm going to do this is by so one thing that's tricky to do here is find the right way to communicate the ideas. I don't really want to just plug in. I mean, if you think about it, okay, if you plugged in 1 on the left side, 1 on the right side, you'll get 1 equals 1. 1 equals 1 isn't a very good, it doesn't communicate very much. What I want to say is that the left-hand side is equal to the right-hand side. So I want to compute the left-hand side. The left-hand side is going to be the sum of 1 plus 2, like 1 up to 1. All the numbers between 1 and 1. So it's just 1. This notation now becomes a bit misleading, right? Because if I want to sum up from 1 to 1, there is no 2 and 3. But is that kind of clear? I mean, we're adding up all the numbers between 1 and 1, so it's 1. The right-hand side is going to be 1 times 1 plus 1 over 2, which turns out to be 1. So left-hand side equals right-hand side. Therefore, the claim is true for n equals 1. This kind of way of explaining things, I think, is a pretty, it's going to be a pretty good way for you to do it on assignments or tests or anything like that. To just, kind of compute the left side, compute the right side, and then observe that they're equal. I think what a lot of people do, which ends up losing the marks, is and it kind of makes sense, but they just plug in the left side, they plug in something to the right side, and they end their proof of the basis by saying, 1 equals 1. But I already knew 1 equals 1. That's not like a good conclusion. A better conclusion is that the left-hand side equals the right-hand side. So it's true for n equals 1. Those feel like the same thing, but it's not quite the same thing. So try not to end your proofs by writing something like 1 equals 1. I've proved it, or something. That's, Is that clear? Maybe not. We'll see more examples, but okay. So I've done my basis. Now what you want to do, so there's a few other parts of this. So this statement Pn, we call this the inductive hypothesis. Okay. And then this logical implication that the inductive hypothesis implies the next case, we call this the inductive step. As a general kind of, format for how you write these proofs, so there's sort of basically 4 steps of an inductive proof. Okay, we've already done the first step over there. So 1 is like state and prove the basis. Second is state the inductive hypothesis. So that's what we're going to be doing next. 3, derive, well, let's say the next step. In other words, like Pn plus 1. So the inductive hypothesis is just stating Pn from the inductive hypothesis. So I'll write just IH for inductive hypothesis. And the 4th is just write a conclusion. So I won't cover this up. I think people are still writing, but okay, so in this proof, we've done the first step. We've done the basis. We've stated it, well, kind of stated. I mean, the main thing is to prove it, but yeah. So we've proven the basis. My next step is the inductive hypothesis. So in this case, can anyone tell me what my inductive hypothesis is? Yep, exactly. Yep, yep. So what I'm going to do is I'm going to let n be some number, at least 1, and assume. So with the inductive hypothesis, right? It's a logical implication that we want to prove. We want to prove that this implies that. So what we should be doing is assuming Pn and then deriving Pn plus 1, right? So this inductive hypothesis step is just saying, what is our assumption? So we assume exactly what was said, that this sum is equal to n plus, or sorry, n times n plus 1 over 2. Okay. So just to be clear, I'm not proving that this is true. I'm assuming it's true. And then we're going to prove the next statement. So in terms of like the second step of the inductive proof, this is the whole step, just assuming the inductive hypothesis. So now we move on to the inductive step. Okay. And we want to derive the next statement from Pn. So maybe I'll... So we want to prove that the sum 1 plus 2 dot 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 up to n plus 1 is equal to n plus 1 n plus 2 over 2. So I'm just taking our original statement and I'm just plugging in n plus 1s for n. Okay. Any idea how to prove this? So one hint is that when you're doing induction, I mean, basically you always want to somehow find a way to use your inductive hypothesis, like to prove this equality. Yeah. Well, definitely like the kind of basic approach of taking one side and showing it's equal to the other side is what we want to do. But it's not going to be equal to n plus 1. It's going to be, well, we want them to be equal to each other, but okay, here's the trick. So maybe it's unfair to ask you to do the very first example of induction because you haven't seen this before, but here's the trick. Let's say I write the left-hand side. It's 1 plus 2 plus blah, blah, blah. And I'm actually going to write so the second last thing is n, and then it's n plus 1. And the trick is, if I look at the sum up to n, I know what that equals by induction. I know that I'm already assuming the sum from 1 plus 2 up to n is equal to this. So if I just isolate this, I can say that is equal to n times n plus 1 over 2. So because we're allowed to use this assumption, right? So this is equal to n times n plus 1 over 2 plus n plus 1. And you need to give a reason for this. My reason is by the inductive hypothesis, which we'll just get used to writing as IH. So IH means inductive hypothesis. By the way, if you're ever doing a proof by induction and you don't use the inductive hypothesis, you should be worried because it's probably not a proof by induction if you don't use the inductive hypothesis. So here's where we're going to use it. We're using the inductive hypothesis. Is it clear how I got from this to this? Any questions about that? So, right, I'm just taking this part of the sum, which I know the value of, and I'm plugging that value in. And the rest now is just a bit of algebra. So how do I add fractions? Need to put them on the same denominator, right? So I'm just computing stuff now. So put them under the same denominator. That should be 2 times n plus 1 over 2, right? I can now put these fractions together, and I can do a bit of factoring. And if you think about it, well, I can factor out an n plus 1 from both terms. I get n plus 2, n plus 1, which is the same thing as n plus 1, n plus 2 over 2, which is equal to the right-hand side of what I wanted to prove. Okay, so we set out to prove this, and that's exactly what we proved. So we are done with the inductive step. Okay. And then it all comes down to a conclusion, which is just a sentence. So conclusion, we can write, therefore, 1 plus 2 dot 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 up to n equals n times n plus 1 over 2 for all n at least 1 by induction. Okay, and that completes the proof, and we can write a little square. Okay. Any questions about any of this? Most of what we're going to be doing for a little while is just more and more examples of induction. So if this wasn't clear, then you do have more chances to understand this. Right now, the key thing to remember is these 4 steps. So basis, inductive hypothesis, inductive step, conclusion. Every proof by induction is basically going to have that structure. Okay, let's do another one. So I want to define a sequence of numbers. So let a0 be equal to 0, and let an be 2 times an minus 1 plus 1 for all n at least 1. So this is like a recursive, so this is something we call a, recurrence relation, or, this is a recursively defined sequence. It's like, so to work out the values of the sequence, the nth value is some, comes from the n minus 1th value. So let's say if we've got like a table, so for n equals 0, an is 0. Can anyone tell me what's a1? So a1 should be 2 times a0 plus 1, right? So 1, right? 2 times 0 plus 1. a2 is 2 times a1 plus 1, which is, oh, sorry, this is a2, not an. Anyone? What's a2? I think 3, because what you should do is you take the previous one times 2 and then add 1. So that one's 3, right? a3 is 2 times a2 plus 1, which is 7, right? And so on. Okay. Is it clear what this means, like how you compute the next value of an? Okay, so what I want to prove is that an is equal to 2 to the n minus 1 for all n at least 0. Which it looks like it might be true when you check the first few values, right? Like, for example, 7 is 2 to the 3 minus 1, and so on. But this, of course, checking the first few values doesn't prove it for all n. So, okay. So proof is going to be by induction on n. First step is the basis. Any thoughts what I should do for the basis? It's something a little bit different about this one than the previous example, but yeah. Basically, yes. Although, so the way I've been describing induction so far is like you want to prove it for 1 and 2 and 3 and 4, etc. So everything works the same if you want to prove it for different value, from, let's say, 0. But the thing is you have to basically start with the first case. So the first case might not be 1. In this case, the first case to check is actually 0. So yeah, I guess I should have probably described it in more general terms. Like, if you want to prove something for all n at least some number, your basis is going to be like the first case. So your basis is going to be like, the first case that you need to prove, which is, in this case, it's n equals 0. So here the left-hand side is A0, which is just, by definition, 0, because that's how we defined it. Yep. So that's not really the claim. That's the definition of the sequence. So what we're trying to prove is this for all n at least 0. This n at least 1 is only telling you how to compute an. So the definition of an is that if n is 0, then an is 0. And if n is at least 1, an is the previous 1 times 2 plus 1. So this whole part is just the definition. Well, of an. And this part is what we're trying to prove. This is like, yeah, the claim that we're proving. So you want your basis to be the first thing you're trying to prove, if that makes sense. Okay, so the right-hand side of this equation then, when n is 0, this is going to be 2 to the 0 minus 1, which is 0 because anything to the 0 is 1, right? It's not 0 in particular. So therefore, left-hand side equals right-hand side. And that completes the proof of the basis. So it's true for n equals 0. Okay, my inductive hypothesis now. So for the inductive hypothesis, you always want to start at the last base case, or the last case of the basis. So okay, we only had one. For our basis, we only did n equals 0. So what I'm going to do is I'm going to let n be at least 0 and assume, basically we assume that the claim is true for n, meaning we assume that an is 2 to the n minus 1. Okay. Notice here I'm not starting at, if I wrote n at least 1 here, I'd be in a bit of trouble because we've only proven the case n equals 0. So therefore, I can't assume the case n equals 1 to get the n equals 2 and n equals 2 to get n equals 3, et cetera, because I haven't proven the case n equals 1, right? So you need to, your inductive hypothesis should start, like the smallest n that you assume should be the one that you proved already, right? Because I want to assume something I've proved and derive the next case. So you want to start at n equals 0. So what do we want to prove now? So what are we aiming for in the inductive step? Any thoughts? Yeah, basically the same thing with a plus 1 in it, right? So we want to prove our claim, but in the case where n becomes n plus 1. So an plus 1. We want to show that an plus 1 is 2 to the n plus 1 minus 1. Right? So we're going to assume the case for n and derive the case for n plus 1 from it. So let's start with the left-hand side of the equation. So an plus 1. Well, here's the thing. We know we have some formula for that, right? Well, because of the way this is written, it's maybe not so clear, but this says that if n is at least 1, like the nth term of the sequence is 2 times the previous term plus 1. I mean, if we think of it, So n is at least 0, so n plus 1 is at least 1. So I can write this as 2 times the previous term plus 1. So this is by definition of the sequence A0, A1, dot, dot, dot. Is it clear how I got this? I mean, you could think of this as, if you wanted to, as an plus 1 minus 1, which is an. But really, I mean, the key is every element of the sequence, except for A0, every later element of the sequence is of the form 2 times the previous one plus 1 by definition. Any suggestions what to do next? Yeah. Exactly. Yeah. So we want to bring in our inductive hypothesis. So exactly. So I know the value of an because we're assuming an is equal to this. So I'm allowed to use that. And actually, you better use that because, like I said, if you don't use the inductive hypothesis, then something is probably wrong. So this is by the inductive hypothesis, right? The inductive hypothesis tells me where I've got an an, I can replace it with 2 to the n minus 1. And now the way math works, right? You bring in the 2. 2 times 2 to the n is 2 to the n plus 1 minus 2 plus 1, which now we get 2 to the n plus 1 minus 1, which is equal to the right-hand side. Okay. Just a comment. So 2 times 2 to the n is 2 to the n plus 1, right? Not something like 4 to the n, or I don't know what else people could come up with, but it's 2 to the n plus 1, right? That's how exponents work. Okay. Is this clear? Or any questions about this? Yeah. Oh. Yeah, so that comes from back here, like when we defined how the sequence works. So basically, every element of the sequence is equal to 2 times the previous element plus 1. That's how you should really think of this. It's slightly confusing because here I've got an n, and over here I've got an n plus 1. But if you think of it as 2 times the previous thing plus 1, that's where this comes from. So an plus 1 is 2 times an plus 1, which is like, it's the same thing as saying an is 2 times an minus 1 plus 1. Just the n is in the place of the n plus 1, or vice versa. Yeah. Any other questions? OK, and then we want to probably write a conclusion. Seems a bit redundant, but I think, I think you will be asked to write conclusions to these things. So conclusion is just, therefore, an equals 2 to the n minus 1 for all n at least 0 by induction. I guess the purpose of making you guys write conclusions is because so that you can really demonstrate that you know what you've proved. But yeah. Okay. Any questions about that? Okay. Let's try another example that has an inequality in it, which is a bit of a different flavor to what we've been doing. So we're going to prove that n factorial is bigger than 3 to the n for all n at least 7. Do you guys know what n factorial is? Okay. So just in case anyone doesn't know, n factorial is 1 times 2 times 3 times ... up to n. So proof. So we're going to go by induction on n, like usual. Now there's a few differences between this and the previous examples. One difference comes in the basis. So can anyone tell me what I should be doing for the basis of this? Yep, exactly. Yeah, and that's something we should remember is like the basis is the first case that we want to prove, right? There's a statement here which we're saying is true for all n at least 7. The basis should be the first case we want to prove. Although later we'll also see some examples where maybe you want a few other cases as well in your basis. But for now, yeah, the basis is like, you've definitely got to do the first case in the basis, if not more than that. So yeah, so basically, well, for n equals 7, we have the left-hand side is n factorial, which, or sorry, 7 factorial. Well, okay, maybe I'll write n factorial, which is 7 factorial, which is apparently 50, 40. Right-hand side, so yeah, I mean, you might need calculators for this sort of thing, but right-hand side is 3 to the n, which is 3 to the 7. And who on earth knows what that is? 2187. Okay. And okay, we can tell this number is bigger than this number. So 5040 is indeed bigger than 2187. Therefore, it's this, the claim is true for n equals 7. Okay, because we wanted to show that this is bigger than, left-hand side bigger than right-hand side, and we can just inspect like, yeah, 5040 is bigger than 2187. Okay. So now we go to our inductive hypothesis. Your inductive hypothesis should always be like you're always making an assumption, right? That's what the inductive hypothesis is. So what's my assumption here that I'm going to make? Or what is the inductive hypothesis? Well, I'll start by saying let n be at least 7 and assume something. Any thoughts? Yeah. Exactly, yeah. So you always want to assume the thing that you have already apparently proved for the nth case, right? So if you think of n being 7, we want to assume that n factorial is bigger than 3n, and then we want to get the next case. So yeah, n factorial is bigger than 3 to the n, okay? And note, this 7 should match with this 7, Your base, where you stopped your base case or your basis should be where you start the inductive hypothesis. So the inductive step, what do I want to show in the inductive step? Yeah, exactly, yeah. So we want to show, yeah, the next case. So we want to show n plus 1 factorial is bigger than 3 to the n plus 1. So let's just start by, start on one side of this inequality and try to do something with it, So left-hand side is n plus 1 factorial. Any suggestions what I should even start trying to do with that? A well-defined question, but yeah. Yeah, that's going to be a really nice idea because, you always have to remember what is your inductive hypothesis, right? our inductive hypothesis gives us something we know about n factorial. And if we want to use that, we need to get an n factorial here somehow. And so I would suggest exactly what you said. Yeah. Oh, so so exactly what you mentioned. You can write this as n factorial times n plus 1. Is that also what you were thinking? Yeah. Because that's how factorials work, right? N plus 1 factorial is the previous factorial times n plus 1. And that's brilliant because we've got this n factorial sitting here. And we know we can say something about it by the inductive hypothesis. So I can say that this is greater than, so this part is greater than 3 to the n. And I can just keep this n plus 1 here like this. And don't forget to give reasons for your steps. So that's by the inductive hypothesis. Perhaps I don't really need a reason for this step. This is just how factorials work. But yeah, this step is by the inductive hypothesis. That's not what we wanted to prove, though. So we're not, this is not this. So we want this. Any idea what to do about it? Yeah. Yeah, but you can kind of do that. I kind of want to do it maybe a little bit differently. But yeah, in some sense, it's kind of like that. But there's a sort of art, I think, in math that you'll learn at some point, which is like knowing when you've won, right? In this case, it doesn't look like we've won. When I say win, I mean getting this, right? That would be a win. If we can get this bigger than this, we've won. Here, it's not the right thing, right? But we have won because it's more than we need, right? So, I mean, n plus 1, I know that n is at least 7, so this is actually at least 8 because n is at least 7. So this is like 3 to the n times something which is at least 8. That's a lot bigger than 3. I mean, so we're in very good shape here. So 3 to the n times n plus 1 is at least 3 to the n times 8, which is overkill, right? It's more than we need. This is bigger than 3 to the n times 3, which is 3 to the n plus 1. So if I put this, so I've got n plus 1 factorial bigger than this, and that this is bigger than this. So therefore, if you put it together, n plus 1 factorial is bigger than 3 to the n plus 1. Okay. So I'll let you ask questions if that wasn't clear, but first I'll just write this conclusion so I don't forget. So n factorial is bigger than 3 to the n for all n at least 7 by induction. Okay, so that's my conclusion. Okay, any questions about this? Because I think this is possibly a bit weirder than the last examples. Maybe so I mean, so is it clear what I did here, right? So, we got to this point. It looked a bit weird. It's not what we wanted. We wanted this, right? But the whole point is like, you have to know how to get that, right? And the thing is, I want this to be at least, or this product to be at least this. And we can prove that it is because, n plus 1 is at least 8, because n is at least 7. That was part of our assumption. So this thing is going to be at least 8 times 3 to the n, and that's more than we need. All we needed was 3 times 3 to the n, or 3 to the n plus 1. Okay, so recognizing when to be sloppy and throw things away and how to do it in the right way is part of the game sometimes. You might not always have a beautiful thing that just comes out to the right answer. You might need to do some other steps.